About to start, I would like to introduce Dr. Fabio Cumbo, who is going to give a talk on building vector symbolic architectures with Python. Welcome.
Thank you for the introduction, and welcome everybody. So my name is Fabio Cumbo. I'm a postdoctoral researcher at the Center for Computational Life Sciences of the Cleveland Clinic, and we are going to talk about how to build vector symbolic architectures with Python. Vector symbolic architectures, a.k.a. hyperdimensional computing or high-dimensional computing. So let me spend some words on the background. Let me introduce you some basic concept that will let you understand what hyperdimensional computing really means and how it works. So with just a couple of sentences, we could say that hyperdimensional computing is a system of computing that operates on high-dimensional vectors. So this means that the algorithms based on this computational paradigm are based on vectors, on operations on vectors. So the main idea behind this concept is not really new. So everything started with von Neumann, with his manuscript, The Computer and the Brain, and 10 years later with the perceptron of Rosenblatt, and on the 70s and 80s with the artificial neural nets, the parallel distributed processing, and the connectionism, until a more recent holographic reduced representation. So if this is not a new idea, why are we talking about this today? Well, because today we have the right technology required to build very large systems according to this theory. So we just say that hyperdimensional computing is a system of computing that operates on high-dimensional vectors, and algorithms are based on operations on vectors. So let's define the set of operations, arithmetic operations actually, which are behind this way of computing. So everything is based on 4 simple operations: the addition, multiplication, permutation, and the comparison of vectors. So we can element-wise to vectors, we can multiply vectors applying the exclusive OR element-wise. We can permute a vector, which means rotating the vector by n positions. And we can finally compare the 2 vectors just by estimating their similarity, computing the Hamming distance or the cosine similarity, or whatever other kind of vector similarity. Let's consider this simple data structure at the bottom of the slide. This is just a dictionary, right? It's a mapping between variables x, y, and z, and values a, b, and c. So according to the hyperdimensional computing paradigm, everything must be encoded into random high-dimensional vectors. Let me point you to this research article. It's proposed by Dr. Pentti Kanerva in 2009, in which he deeply explained the arithmetics behind this way of computing. So, okay, let's start with the encoding. So according to the dictionary, we know that x is equals to a. So we have to represent both x and a as vectors. Let's use binary vectors in this case. And we say that x is equals to a. We could bind these two, their vector representations together using the multiplication operator, which just consists of applying the element-wise exclusive OR. And we can do the same with the other two variables in the dictionary, just by computing the multiplication between the vector representation of y and b, and the multiplication between the vector representation of z and c. So we also know that these 3 mappings compose h, which is the variable that represents the dictionary. So we can now collapse all of these information together into a single vector just by applying the addition operation element-wise between the vectors that we just computed. So we can finally convert the computed vector back into a binary vector, just applying some kind of majority voting mechanism. So let's have a deeper look at what we've just seen. So we were able to compute the hyperdimensional representation of our data structure H, and we saw that retrieving information from H, which means decoding H, well, I missed a slide. I'm sorry about that. This one. So let's see actually. So we can even more appreciate the power of the binding operation on the retrieval of values, the values that we just computed. And if we essentially bind h with x, we are going to indeed produce a new vector, which is pretty similar but not identical to the hyperdimensional computing representation of A. We will see in the next slide why actually the produced vector is not identical to A. And we can verify that the produced vector is almost A, just by searching for the closest vector among all the hyperdimensional representation of the values A, B, and C, just by computing, again, the M-in distance or the cosine similarity or whatever other similarity measures on vectors. So again, let's have a deeper look at this. We were able to compute the hyperdimensional computing representation of the data structure H. And we have seen that retrieving information from H, which means decoding H, is extremely simple, extremely easy. So in the previous example, we saw that binding H with X produces a vector which is very similar to A. And let's see why it's not actually A, but something very, very similar to A. Let's decompose the binding operation between X and H. And we can say that H is actually the sum of the three bindings XA, YB, and ZC. So we can bind all of them by X, because the exclusive OR distributes over the addition. And, well, X and X actually cancels out, just because the exclusive OR is its own inverse. And we can say that XYB and XYC, we can consider that just noise, some kind of noise, which means that these bindings actually produce vectors that are dissimilar to any known vectors, and so they are essentially approximately orthogonal in the same space. So the final result is something very, very similar to A. So yeah, we can conclude this introduction to the hyperdimensional computing with these observations. So essentially, a randomly chosen vector is dissimilar to any other vector seen so far because they are approximately orthogonal. The addition produces a vector that is similar, and the multiplication and the permutation produce vectors that are dissimilar to the input vectors. The multiplication is invertible and it distributes over the addition. Permutation is invertible and distributes over both the addition and the multiplication, and the multiplication and permutation preserve the similarity. So these are the main characteristics that we need to take into account when we want to shape some kind of reality into a hyperdimensional computing model. So let's see another example. This is actually the same example in the Canerva's paper, where he first introduced the concept of hyperdimensional computing. What's the dollar of Mexico? So we want to determine a currency, of a specific country. So let's extract a few information from this question. We know that dollar is in general the currency of the United States, right? While peso, which will be the answer to our question, is the currency of Mexico. So let's try to encode this information following what we just learned. So encoding everything into random high-dimensional vectors. So here, currency, country, and let's add other information that help us shape the reality we want to encode. So let's add, for example, capital city. Well, all these variables are vectors. So what about their values? USD and PES, peso, are both vectors. USA and Mexico are both vectors. And Washington, D.C. and Mexico City are both vectors. So our goal here is to try to build a vector representation of the two countries. So let's start with the United States. We can bind the vector representation of the variable country with the vector representation of the value USA. We can bind the vector representation of the variable capital city with the vector representation of the value Washington, D.C. And we can bind the vector representation of the variable currency with the vector representation of the value USD. So just remember that binding two vectors is equal of applying the element-wise multiplications between these two vectors, so which is the element-wise exclusive OR operation. So we can finally bundle all these vector together, which means applying the element-wise sum of the vector to build a new vector, which is actually the representative of the country United States. And we can do exactly the same for building the vector representation of the country Mexico. So let's say that we want to have a vector representation for the world we have just defined, just composed of the two countries, United States and Mexico. Well, we simply bind these two vectors to produce the final vector symbolic architecture. So let's try to answer our question, what is the dollar of Mexico? We have a vector representation of our architecture that we defined as the binding between the vector representation of the United States and the vector representation of Mexico. So if we decompose these two vectors, the result of the binding is something like this, where country binded with itself cancels out just because of the exclusive OR operator, and the same for capital city with itself, and currency with itself. So what happens if we try to bind this vector representation of the vector representation of USD with our architecture? This produces a new vector which is different but very, very similar to the vector representation of PES, peso, which answers our first question. So everything we've just seen is implemented in the hdlib library. It is open source, is available on the Python package index as well as in Conda. Well, this slide shows its architecture, its modules. It's very simple. Starting with the space module, which contains the definition of the space and vector classes. And well, obviously, the vector class is used to build vectors with a certain size, a certain length, a certain type, could be binary or bipolar, with similar characteristics. And the space class, which is used to build some kind of container for a multitude of vectors, with methods that allow to easily search and retrieve in the space for specific vectors according to some specific criteria. Of course, vectors also implement the three arithmetic operations that we just defined some slides ago. And the same operations are also implemented in the arithmetic module. So let's jump to some kind of practical application of this computing paradigm. We used it to build a classification model. So let's have a look at the algorithm. We say that in hyperdimensional computing, every atomic element is associated to a d-dimensional vector, right? So in general, in a data set, you may have some numeric values. Well, all of them must be encoded into vectors in a high-dimensional space. And all these vectors represented a dictionary. So without this dictionary, the classification model is practically useless, right? Because it will not be able to map the values of the data set to vectors in the hyperdimensional space and back to the actual number in the data set. So, and the set of encoded vector, which represent the content of our data set and represent the data dictionary of our model, is also called the set of hyperdimensional levels. So we start now processing our samples by grouping them by their class. This is a classification problem. Let's consider a binary classification. You have two classes and a bunch of samples for each of the class. So for each of the samples, we need to build a vector that we finally need to sum, and we finally need to sum all of these vectors together to create the hyperdimensional representation of their class. So we create a hyperdimensional representation of the experiment, of the sample, just by encoding the feature content that we previously encoded in our data dictionary. And we are also able to encode the position of the single feature in the dataset just by rotating its hyperdimensional vector representation n times, with n equals to the actual position in which this feature is located into the dataset. So we have a vector representation of a sample for a specific class, and we sum this vector with all the other vector representation of the other samples belonging to the same class to build the vector representation of the class. So what is the problem now? The problem is that the more vectors we add, the more noise we introduce into the model. So how could we minimize the model? So with a process called retraining. So what does retraining mean? It means that we have the vector representation of a class, and we iterate over the samples that belong to that class in the training set. So the same samples that we use to build the class vector, and we try to predict their class. So now this means that we are going to compute the cosine similarity or whatever other kind of similarity measure between vectors. Between the vector representation of the samples and the vector representation of the class. So since we use the same samples to train the model, we would expect a correct classification. But again, this model is very noisy at this point. So what we do in case of a misclassification? We element-wise subtract the vector representation of the sample from the incorrect class, and we element-wise sum the vector representation of the sample to the correct class vector, just to decrease and increase the signal of the sample. And we do this for each of the samples in the training set iteratively until the error rate doesn't change anymore. So we are not going to be able to further mitigate the error rate. So at this point, we have an optimized model composed of a vector for each of the classes in our data set. So what's next? Well, this is a classification model, right? So we want to do prediction. How could we use this model to do prediction? We could do the same process we did for the retraining. It means that we iterate over the samples in the test set at this point, and we compute, again, the cosine similarity or any other kind of similarity measure between the vector representation of the samples and the vector representation of the classes that at this point represent our model. So the closest class is the prediction. So could we also do feature selection with this kind of model? There is nothing in literature about that. It's actually a bit tricky. There is something we could use around our model that is actually, I would say, the easiest way to do feature selection. It works with every kind of classification model. That's the stepwise regression. So a stepwise feature selection can be defined as a backward or forward variable elimination. And here we're going to look at how the backward variable elimination works, but analogously, the forward variable elimination works in the same way. And here is a pseudocode, but it's probably better to look at the graphical representation of the algorithm, like this one. So consider that we have a data set with a certain number of samples and a certain number of features. Let's say 5 features in this case, a very small, a toy model. So what I want to do as a first step is to split the set of features. We said we have 5 features, so into 5 models with 4 features each. So essentially every model is going to miss a feature. And we build the model in the same way we did before. And we evaluate these models. So we could evaluate these models according to the accuracy, for example. And we can focus on the models with the best scores, the best accuracies in this case. So at this point, starting with the features resulting from the intersection of the features used to build the best models, let's say that 2 models got the best accuracy here. We keep going generating other n models, each with n-1 features. And I keep going generating models with a smaller set of features until we are not able to build models with a good accuracy that we could set a priori. We could set a threshold, 70%, like in this case. So this is an iterative process, and we are essentially assigning, we can essentially assign a score, an importance score, to every feature according to the iteration where they get discarded. So let's see the hdlib architecture again. We also implemented the model module with a definition of the model class, which helps in building a machine learning model following the hyperdimensional computing paradigm, and eventually performing a stepwise regression to do feature selection. All right, let me jump to Galaxy. I think most of you already saw something yesterday. So what is Galaxy? Let me introduce Galaxy. This is an open source browser-based platform for the management and analysis of biomedical data. It's a worldwide community project, so there are plenty of research groups that are actively work and contribute to the development of the platform worldwide. It integrates a workflow management system with the aim of making tools accessible to the researchers without any programming skills. And well, I'm a member of the Galaxy team here at the Cleveland Clinic, and my PI, Daniel Blankenberg, is one of the first developers of the Galaxy platform since 2005. Most importantly, it runs over the Access cluster, which is the inter-university high-performance computing cluster in the United States. So you essentially have access to computational resources for free if you run your analysis in Galaxy. And if you ever worked on bioinformatics, for sure you heard about Galaxy. Let's look at a few numbers very quickly. If you're wondering whether it actually works and whether people is actually using it, I think these plots speak by themselves. So in 2020, we reached over 2,000 publications citing the Galaxy project, with over 15,000 citations in total. So there is a main server on which the public instance of Galaxy is running, but it's actually something that you can download and run on your own server. With your tools, using your computational resources. So the first plot on the left shows the actual number of public servers running Galaxy worldwide. It's over 150 now. Well, there are plenty of bioinformatics tools already available, already integrated into the platform, but generally tools are hosted on the Galaxy toolshed, which is a repository of tools. Actually wrappers for existing tools. And yes, we reached now about 10,000 tools wrapped and ready to use on the Galaxy platform. So let me also quickly mention that every year there is a Galaxy community conference somewhere in the world. It's a unique opportunity to network with other people who are actively involved in the development of the platform, but also with people who are simply interested in integrating their analysis frameworks into the platform. So the last conference has been in Brno, Czech Republic, last July. Well, the next year will be somewhere else in the US. You're all invited to join. So coming back to our library, we built a wrapper for Galaxy around a tool called Chopin 2 that actually implement the machine learning model and feature selection technique with the support of hdlib. The tool is fully integrated into the platform. It's also available on the main instance of Galaxy at usegalaxy.org. So again, hdlib is open source. Its code is available on GitHub. If you're interested in playing with vectors, I would encourage you to install it, to open the wiki. There are a few examples, including the very basic one, what is the dollar of Mexico, and also a step-by-step guide on how to build a machine learning model and how to do feature selection as a stepwise regression. Well, as I mentioned, it's also available in Conda, where we reached almost 3,000 downloads pretty recently. We also published the paper last year on the Journal of Open Source Software. So if you are planning to use the library, please give it a credit. And of course, remember to leave a star. So just another quick note. Let me start this video. So another quick note. At the Cleveland Clinic, we got a 10-year partnership with IBM. We installed a quantum computer in our department. It's the first quantum computer that has been installed outside of an IBM data center, and it's going to be used exclusively for biomedical research. This is a short time lapse that shows the setup, and well, we currently have an open discussion with IBM trying to figure out how to do hyperdimensional computing on a quantum hardware. We know it's possible. We have all the ingredients to do that. We know how to encode vectors in a quantum space. We know how to apply these arithmetic operations, since it's just linear algebra. And we know how to compute the cosine similarity between two vectors on a quantum hardware. So we know it's possible, but we're currently trying to figure out whether the current number of qubits is enough to do this kind of operations. Currently, we have 127 qubits. So your question here could be, what is the actual advantage? What is the actual benefit of doing hyperdimensional computing on a quantum hardware? Well, we hope that in the context of a classification model built according to the hyperdimensional computing paradigm, it could increase its accuracy. But at this stage, this is just a speculation. And that's all right. That's pretty much all. Thank you very much for your attention.